Hello, ITCS participants. I'm Jane, and I'm going to be talking to you about some joint work with Mingda at UMass Amherst on the limitations of membership queries in the testable learning model of pack learning. So in pack learning, there are two major settings that are very widely studied. There's distribution-free pack, where you make no assumption on the distribution over inputs, and there's distribution-specific pack, where the distribution is known and is often nice, such as the uniform distribution on the Boolean hypercube, or more generally, product distributions. In the distribution-free setting, there are lots of strong lower bounds because the distribution can be arbitrarily complex in the worst case. In distribution-specific pack, a lot more learning is possible, so more expressive classes can be learned efficiently, but it's limited in practical relevance because, well, real-world data doesn't necessarily come from a nice distribution. So one goal of the testable pack model, introduced by Rubenfeld and Vassilian in 2023, is to capture a lot of the benefits of the distribution-specific setting while also recovering some of the practical relevance. So part of distribution-specific pack that makes it more fragile is that the guarantees only hold when a distribution satisfies a property. That property is assumed. In other words, the distribution comes from some supported family. Otherwise, the learner's behavior is completely undefined. In testable pack, we're trying to make it a little bit less fragile, in that the distribution can be anything, but the learner doesn't have to output a hypothesis on just any distribution. It can reject data if it doesn't think that that data comes from a supported distribution. However, whenever the learner outputs a competitive hypothesis, in other words, whenever it accepts the input instance, that hypothesis has to be competitive over the unknown distribution. So in the testable agnostic learning problem, we need an algorithm that satisfies two guarantees, soundness and completeness. The soundness guarantee says that whenever the learner outputs a hypothesis H, it satisfies that the classification error is at most opt plus epsilon, where the probability is over the unknown distribution D, and opt is the distance from the labels y to the closest function in the desired concept class. The other guarantee is completeness, and completeness says that if D actually does have the desired property, then the learner outputs a hypothesis with high probability instead of rejecting the instance. So now we're going to switch topics a little bit and talk about the power of membership queries. So in typical pack learning, you just get random examples and then you have to output your hypothesis. And we also have the membership query model, which is a stronger access model, where in addition to samples from the distribution, a learner can also make black box queries to the labeling function. So Feldman in 2009 showed that membership query access can make learners more efficient in the distribution-specific setting, but not in the distribution-free setting. So there's an explicit separation. There's a concept class that's easier to learn with membership queries on the uniform distribution. But in distribution-free agnostic learning, you can simulate membership query learners with just random examples. One of the advantages of membership query access is that it makes it easy to detect relevant variables, as in variables that the function actually depends on. This makes it easy to learn things like the class of sparse parities, which are functions of the form the parity of xi for I in some set of size k. This is a problem that's widely believed to be hard, with noise requiring n to the omega of k time to learn on the uniform distribution. So as a result, a striking advantage for membership query algorithms exists for lots of natural concept classes because they contain k parities as a subclass. For example, k-juntas, which are just functions that depend on k variables, and depth k decision trees. So since it's known that membership queries are helpful in distribution-specific learning but not helpful in distribution-free learning, it's natural to wonder whether there's any membership query advantage in testable learning. So here we're going to consider the testable learner with queries, which has sample access to the unknown distribution and membership query access to the labeling function, and we're going to ask how much can membership queries speed up the task of testable learning? In brief, the answer is not much. This brings us to our first result, which is that if a concept class C is agnostically testably learnable with queries in time t over some distribution d, then it's agnostically learnable with random examples in time polynomial in t over d as well. So to make that a little bit more intuitive, testable learning with queries is as hard as agnostic learning with random examples in the distribution-specific setting, where the distribution-specific learning and the testable learning are with respect to the same distribution. So this yields a corollary under the assumption that learning sparse parities with noise is hard. Because learning sparse parities with noise is assumed to take n to the omega of k time on the uniform distribution, this means that no concept class containing k parities as a subclass can be testably learned in n to the little o of k time over the uniform distribution, even with membership queries. To prove these results, we're going to use another task as a bridge between distribution-specific learning and testable learning with queries, and that's a task that is typically called refutation. We're going to show that sample-based refutation reduces to testable learning with queries while dropping the query access. So basically, if you have some algorithm that does testable learning with queries, we can simulate the queries to that algorithm in order to solve refutation with samples. Here's a little diagram of how these tasks relate to each other. Previous work showed that sample-based distribution-specific agnostic learning and sample-based distribution-specific refutation reduce to one another. And in this work, we're going to show that refutation reduces to TLQ. So in other words, an algorithm for TLQ yields an algorithm for sample-based refutation. All of these arrows represent reductions in polynomial time. So refutation is essentially distinguishing a sample that comes from the concept class C versus a sample of just random bits. So we're going to take a sample of points where the x's, these are points x, y, so labeled examples, where the x's are drawn from the distribution we care about, which is D. And the refutation algorithm outputs either noise or structure with a soundness and a completeness guarantee. The completeness guarantee says that if the examples come from C, the concept class, then we have to output structure with probability at least 2/3. And if the labels are just random, then we must output noise with probability at least 2/3. For the rest of this talk, we're just going to let D be the uniform distribution. So all refutation is going to be with respect to the uniform distribution. So this seems like it really should be an easier task than learning, right? If you have a learner, you should be able to perform refutation. And that's certainly true if we have a learner that doesn't require queries. We can just split the samples into training and test sets, run the learner, and test its error. If the error is high, it's noise, and if the error is low, then it comes from the concept class. But instead we have a TLQ algorithm, which requires query access, so we're going to have to answer queries. And essentially what we're going to do is just answer the queries randomly. So here's a sketch of a refutation algorithm that uses TLQ as a subroutine. First, we'll draw a random function f. This is just a random function, random Boolean function over the hypercube. Whenever the TLQ algorithm wants to make a query, we will answer it according to this f. So that way we don't have to make any queries, we're making internal queries to a function that we generated ourselves. Then we'll draw the samples for the refutation instance, and we'll filter the samples to just points x, y, where y equals f of x. Throw the rest of them away. So essentially we're drawing from the uniform distribution over the subset of the Boolean cube where y of x agrees with f of x. Then we'll split the samples into training and test sets, run the TLQ algorithm on the training set, and measure the error of the hypothesis with respect to the test set. If TLQ returns a bad hypothesis, i.e. a hypothesis with high error, we will return noise, and otherwise, so this is the case where we get either a good hypothesis or a rejection, we'll return structure. So let's analyze this algorithm and make sure that it performs correctly. So let's suppose that we're in the noise case, which means that by the soundness guarantee, we need to output noise with probability at least 2/3. So in this case, the samples are drawn independently from Bernoulli 1/2, they're just coin flips. We're filtering the samples to points where y equals f of x, but since the y's are random, that means that each sample is filtered out with probability 1/2, independently of x and f. So thus, the distribution of samples is still uniform over 0, 1 to the n. Think of it as just drawing some x from 0, 1 to the n, throwing it away with probability 1/2, probability 1/2 keeping it. Clearly, the distribution is still uniform, even after this filtering. So by the completeness of the TLQ algorithm, since the distribution is actually uniform, it must output a hypothesis. But since the function is random, since the test set is just a bunch of random bits, the hypothesis is going to have error close to 1/2. So when this happens, we will output noise and that will be correct. Now we'll give the completeness guarantee for the refutation algorithm, where the samples for the refutation instance are x, y, where x is uniform, and y is a label from a labeling function that belongs to the concept class C. So in this case, after we filter the samples to just instances where y equals f of x, the distribution may no longer be uniform over the hypercube. So the testable learning algorithm might reject the instance. However, we said that if we receive a rejection, we will output structure, and in this case, that's correct. If TLQ returns a hypothesis, then by the soundness guarantee for testable learning, it must have error at most epsilon with respect to the distribution that its samples come from, which in our case is not uniform, but is the filtered distribution, the distribution over points where y equals f of x. Both the training and the test data come from this distribution, so the test error should be at most epsilon with high probability. In this case, we also correctly output structure. So to recap the strategy, we're building a refutation algorithm from a testable learning algorithm by answering queries according to a random function and filtering the samples to points where the refutation samples agree with the random function. The blow-up in time complexity is just a small polynomial, so this means that any polytime algorithm for TLQ yields a polytime algorithm for refutation over the same distribution that TLQ is defined with respect to. Previous work builds a distribution-specific agnostic learner from a refutation algorithm, also with polynomial time blowup. So, if a concept class C can be learned over some distribution D in the TLQ setting, then C can also be learned over D in poly T time with just random examples. Now we're going to move toward our next result, which is a stronger lower bound for a more specific class of membership query algorithms. So as I mentioned earlier, there are some classic well-known learning algorithms for junta-like classes, so classes that contain k-juntas, on the uniform distribution that are much faster than their random example analogs. However, these algorithms all make very limited use of membership queries. Typically, the queries are used to determine how relevant variables are. That's this influence estimation task. Or queries are used to estimate the mean of some function under restriction of the hypercube, so estimating the expectation of f of x where x comes from some large set S. So these are not very targeted membership queries. They're basically just using the queries to create some distribution and estimate some quantity over it. Basically, you're using the queries to take random examples from some other distribution. If you're familiar with the statistical query or SQ model, you might notice that these quantities look like SQs over different distributions or even different domains in the case of estimating influences. So, for example, in the mean estimation under restriction case, we're estimating the mean of f, where the distribution is just uniform over the set S. In the influence estimation case, the distribution is uniform over the set of edges in the Boolean cube, so the set of pairs that differ by 1 bit, and the labels are whether f of x and f of the neighbor disagree. To capture the use of membership queries in these classic learners, we put it into a type of statistical oracle model similar to the SQ model. So SQ learners are those that can be implemented in a way where you can replace the sample access with queries to some oracle that answers questions about correlations between the unknown function and a test function of your choice. So MQSQ, or Membership Query Statistical Query, which is a thing that we made up, is basically that, except you can also customize the distribution that you're taking the correlation over. So it includes all the type of SQ-like quantities that you can estimate that require membership queries. So we show that all of these algorithms that we discussed, the classic algorithms for learning juntas and decision trees, etc., with membership queries, can all be implemented with an MQSQ oracle. And in order to give lower bounds for testable learning, we show that any testable learning algorithm in the MQSQ model yields a refutation algorithm in the SQ model. And we also show the reduction from learning to refutation, so we show that an SQ-based refutation algorithm yields an SQ-based weak learner, and that gives lower bounds that come from the SQ dimension. So here's our second result. If a concept class C is agnostically testably learnable with T MQ SQs over some distribution D, then its SQ dimension is poly in T as well. So this means that we can get some bounds for specific MQ algorithms even if learning sparse parities with noise is easy, because there is an n to the omega of k SQ lower bound for learning k parities. So even if LSPN is easy by some non-SQ method, none of these efficient membership query-based algorithms for learning concept classes that contain k parities can be quote-unquote made testable, or like easily made testable, without introducing some non-MQ-SQ use of membership queries. So I'd like to close with some discussion and an open question. We've shown that membership queries are limited in that they can't make testable learning easier than distribution-specific agnostic learning. However, this doesn't completely close the book on whether membership queries have any power in testable learning at all, because we're not comparing testable learning to testable learning. So a very natural question is whether testable learning with membership queries is easier than testable learning with samples. We don't show this, that's still an open question. It would require a stronger bound for testable learning with queries than anything that can be obtained through our technique, which is going through refutation. And the reason for this is that there are classes for which TL with samples is hard, there are lower bounds, but refutation with respect to the uniform distribution is easy. An example is the class of monotone functions on the uniform distribution. There's a 2 to the omega of n lower bound for testable learning, but refutation can be done in 2 to the square root n time. So I think this is an interesting question. There's definitely still more to investigate about queries and testable learning. I hope you found this video interesting, and thank you for watching.